Hello everyone, my name is Newton, and this will be the first video of many where I go over my thought process and my going through the umpire steps while solving Leetcode problems. In this video, I'm going to start with the jump game problem. Here's how the problem goes. You are given an integer array nums, where each element nums at I indicates your maximum jump length at that position. We want to return true if we can reach the last index starting from index 0, or false otherwise. So right away, let's get to understanding this problem. We know that the input and output are an integer array called nums and a true or false value. And what this true or false value represents is, can we reach the last index, or in this case the last index is just length of nums minus 1 from position 0. Now, another thing we always want to do when looking at problems is considering the context, the constraints. So what should we take a look at? We note that all of the numbers, all of the jumps themselves, since nums I indicate maximum jump lengths at each position, let me write that as the input actually. Nums I represent maximum jump lengths. So nums of I is always going to be non-negative. So there's no situation where where one of these elements in nums will be a negative number, which would cause us to jump backwards. So nums I is always non-negative. This also tells us some pretty valuable information about the problem and the solution and what we can do, but I'll get into that in a few minutes. Next, we have that that num's length must always be somewhere from 1 to 1,000. So there's always going to be at least one position. So nums must have at least one position. And what this tells us is that we won't have edge cases where we receive an empty array or something like that. But this does also create another edge case, which I'll also get into in a minute. So other than that, what context can we derive from how the problem is written? Well, because all of the numbers in nums I are always not negative, we know that we're always going in the same direction. Direction to right. And we also know that we want to reach the last index starting from index 0, or false otherwise. And here's a question that we need to answer, which is, when do we return false? And we return false when we cannot reach the last index starting from index 0. And how do we know that we can't reach the last index anymore? I would say that must happen when when we reach a nums I which equals 0. And I say this because if nums I is 1 or greater, you'll always be able to jump to a new position. The only time where you get stuck and you can't move any further and must return false as a result is when nums I equals 0, when the position itself is 0. So now let's get into some edge cases. Here's some that I want to take a look at. So we know that nums must always have at least one position, but what happens when nums has exactly one position? Then you'd start off at the final index, wouldn't you? If the length is 1, then length of nums minus 1 is just 0. So in this case, we would return true. Now, as for this problem, the constraints don't really make room for more possible edge cases. So I think that'll cap off like our edge cases for this problem. So now let's get into the planning. And there are a few plans we can consider here. Here, let me write down a plan that I would consider to be a brute force approach. This plan would just start with where you'd start at index 0, and you just test out every possible path from 0. So every possible jump that you can make. And if any of your paths reach the final index, you would return true. This is a very, very inefficient approach, though it could work. So due to its inefficiency, we should definitely look at a different plan. So another plan that I've been thinking of with this problem is the greedy approach. We know that we can only move in one direction, and that we can move in one direction, and we want to maximize potential. And we can split this problem into many bite-sized subproblems. For example, this can be split into what is the most efficient jump from my one location. We're always going to look for the local maximum here because with the way that the nums represent the maximum jump lengths, you can jump from any number up to nums at I, but you're not limited in any way to only having to jump to nums I. There isn't going to be a situation where choosing a smaller number could lead to a better outcome, or where choosing a larger number pigeonholes you into an inefficient approach. So if we can answer what is the most efficient jump from my one location any number of times until we reach nums at I equals 0, a pit, or we reach the final index, then that would tell us in a pretty surefire way what is the answer to this solution. Is it true or is it false? Can we reach the final index? And here's something I wanted to note about this problem. It should only be constant space. However, in terms of big O notation, it has the potential to be quadratic in its time complexity. And let me explain why. With this forward approach, we can run into many situations that cause us to pretty much evaluate n over 2. And that's because if we're trying to constantly answer what is the most efficient jump from my one location, we're pretty much checking every possible jump. If we iterate forward and we want to see which jump takes us the most distance or secures the most distance by jumping on the next larger number, we're we're setting up the stage to where we're going to be comparing every possible jump from potentially every possible location. So here's an example where that could probably mess things up. Let's say okay. Let's say okay, this will be our edge case example that causes like a lot more inefficiency. So right here, if you look at this problem, you can see that this should definitely return false, right? Even in the most efficient possible jump from the rightmost 4, we won't be able to reach the end. We will definitely fall into a pit. And every possible jump that could lead to this most efficient jump is also going to lead to a pit because they can't move any further than this jump. The farthest possible jump does not reach the end. So we know that it would return false. However, what if we follow the algorithm we went over in this plan, what will the time complexity be? Well, we start from the first position, and then we take a look at what's the most efficient jump. So we compare what do we get from jumping to the first position? Well, we move forward 1 spot, and we gain a potential of 4 spots from getting to that position. Okay, which gives us an efficiency of 5 spaces. Provides a total distance of 5 spaces. We can then compare it with all the other possible jumps that we have access to from the first location. And here's something we need to note. We're essentially checking we're checking multiple different jumps that in this case are equally likely to succeed. When in reality, would we really need to do all of that? This could lead to some situations where we're essentially looping over all of the potential jumps twice just to get an answer to a subproblem that increases the complexity. So let me suggest my third plan, which is the greedy approach, but we iterate backwards. So what if instead of starting from index 0, we started from the final index and we moved backwards? Let's take a look at another approach. We know that each of these jumps could easily cross the final finish line, right? And of course, one way we can solve this is simply going, okay, well, 9 is greater than the distance between this location and the final location. But one thing that doesn't account for is that it could potentially compare many jumps that would have the same level of the same likelihood of completing it, when we don't really need to do that. If we iterate backwards, we're only focusing on a jump that could reach the goal. And let me show an example of that. Let's use the example in the first. Let's use the first example. So let's say we start off at the end. Let's say we start off at the end. If we iterate backwards, can we find a jump, any jump, that can reach this position? Well, when we iterate backwards once, we see that 1 can reach this position. So reaching 1, in this case, would have the same outcome as if we straight up reached 0. So by that logic, why do we even need 0 anymore? All we know is that once we reach this position at 1, we've succeeded. Now the question becomes, is there any position where we can jump to this number, 1, which we know is equal to a success? Well, we go back 1, we don't see any potential, we just see a pit, we don't see any potential to get to 1 with this 0, so we iterate backwards again. Here's 2. With this 2, we can get to our winning position, which is 1. And if we know that we can reach the winning position from 2 now, we don't need to find any other position if we know that 2 will lead to the winning solution. So now, how do we get to 2? Is there a number that gets to 2? Well, we have 1. And that gets us to 2. And because 1 is located at the 0th index, that tells us that there must be a solution from 0 to the final index. And with this approach, we only iterate through the list once. Let me try it with our example here. So we see that our final goal is this 0 at index 9. And let's iterate backwards and see if there are any numbers that can jump to it. 0 cannot jump to it. 0 cannot jump to it. None of these zeros can jump to it. This 4 cannot jump to it. Neither can this 4, or this 4, or this 4, or this 4. And now we've reached the 0th index. That tells us that there are no jumps that can reach the final index. The numbers that are here can be any sort of numbers from 1 to 1,000. But if the whole combination of numbers does not reach the final index, they do not matter. We need to only focus on the jumps that matter, which are the jumps that connect to the final index. So with that in mind, how can we code our solution? The solution has become much more simple now. Here's the algorithm. We start at the final index. We iterate backwards in a for loop, because we know we only need to look at each number once. We keep track of the new goal, essentially, of what is the new position that we need to hit in order for our input to return true. And then we exit the loop. And that could be achieved in a very, very quick implementation. Sometimes you have to really think about a problem to figure out how to solve it in the most efficient and the most simple way. So let me get started. Let's start off the goal as the length of nums minus 1. In range okay, let's iterate backwards. I need to refresh myself on how to iterate backwards in Python. The only thing that comes to my mind right now is the is the backwards iteration for Java, which is a mistake. Well, then how to iterate backwards in a for loop. Oh, so it is simply a range with a negative step. Okay, that makes more sense. So let's do this. Length of nums minus 1. Here's our goal position, which actually, we know we've already hit our goal position. We don't need to recheck our goal position. Let's change this to length of nums minus 2. And then we want to iterate till 0. So let's set our end to -1, and let's set our step to -1. Now let's say if nums at I plus I is greater than or equal to goal. What this means is that the position that nums of I is the position I, and the jump potential at position I are enough to reach the goal. So if that is the case, then let's set I to the new goal. The new goal is the position I. And now, once we exit the loop and we've searched every number, if the goal is now 0, as in we've iterated through the whole list and we've found that we can reach the winning solution from 0, then we return true. If not, we return false. So how about we return goal equals true? Now let's take a look at this problem. There isn't much to review here besides our approach. And at this point, I would consider writing test cases, but thankfully with Leetcode and Neetcode, we don't have to do that. As we can see, our case has been accepted. And let's submit it. And we have completed this problem with only five lines of code. So I think I already went over this, but of course the final step of umpire is to evaluate your solution. Just so you know and you're keeping track of how quick your approach is, and how much time and space you're using. So O of n time and constant space. Well, with that, I think we've reached the end of this video, and yeah, that was a much better solution than my first approach at this problem, of course. And I think going over this problem and hashing out all of the potential plans and why this one works and this one doesn't can really help me think about the problem in greater detail. And it can help me apply this problem to future problems that I potentially see at interviews. So, thank you very much for watching. This is the end of the video.